In the previous video, I mentioned we were looking at algebraic functions, and so now we're going to look at what are called transcendental. But let's look at what we just did. So we went through 1 through 6, and these functions are all called algebraic because these are algebraic operations that I'm doing. Powers, sums, quotients, even roots are considered algebraic. But let's look at these last few exponential functions, for example. So here's a typical example of an exponential function. 2 to the x. There are values that I can plug in where this makes sense, and algebraic operations can be used to describe them, like 2 squared means multiply 2 times itself. But then you get some, and 0 and negative powers. We can make sense out of all of those. We've defined all of those in algebra. But what does it mean to take 2 to the square root of 2 power? So that gets a little tricky. I don't know what that means. So that number is what we call a transcendental number. These are algebraic numbers when I can make sense out of them algebraically, but that's a transcendental number. And so this function, because it generates some numbers that we can't describe algebraically, that's called a transcendental function. Well, it turns out if you start plotting f of x equal 2 to the x, its basic graph is going to look something like this. It's exponential growth. It's doubling. Every time I put in an x that's one unit further along, it's going to double. So starting out at 0, it starts at 1, and it doubles and doubles and doubles and doubles as you go out. And it going this way, you can think of it as being cut in half as I'm going to the left. But it's still doubling as you go from left to right. That's your basic exponential growth. And this is very steep growth. But this is sort of the graph of any a to the x if your a is bigger than 1. It's just that if it's 3 to the x, well then 3 to the x is actually going to be tripling. You'll still hit this point, but then it's going to be tripling. It means it's going faster. And then it's going to get to 0 faster over here as well. 4 to the x, 10 to the x, all of those. Well, there is a special one that we use a lot in calculus, and that's e to the x. And e to the x, well, since e is the number, it's about 2.71828, and it keeps going 1828, 1828. So e, it's an irrational number, and it lands between 2 and 3, closer to 3. So e kind of comes in here like this, something like that, and then it's between them on this side as well. But it's still an exponential growth function. All of these functions, just looking at the graphs, we can see that I'm not restricting the domain, even though I get some weird numbers that we call transcendental numbers. I'm still going to allow you to plug in these weird numbers. And then the range on all of these, you can see is you'll never get to 0, and then it goes to infinity. So it's 0 to infinity. So we have a corresponding f of x equal to 1/2 to the x. And what happens here is this is the halving function, meaning it cuts it in half as I go from left to right. It'll still hit this point, but it's going to keep cutting it in half. So it sort of reverses this one above. And it turns out the domain and range are still the same. But this is the graph for all functions, or sort of this shape for any a to the x, where we always have a bigger than 0, but between 0 and 1. So 1/2 to the x, 1/3 to the x, 0.9 to the x. They all sort of have this shape. And the farther from 1 that you are, then the steeper it gets this way. So this would be like 1/3 to the x. The closer you are to 1, then the flatter it gets. And same way here, the closer I get to 1 on this side, if I get 1.1 to the x, it's going to be fairly flat. But it's still exponential growth. So we have sort of two classes, exponential growth, exponential decay. So that's our first transcendental function. And then corresponding to that, which if you should have learned in pre-cal, are these functions called the logarithms are the inverse functions. And these are totally transcendental because there are times we can do some calculations with them, but the functions are just sort of made up. We make up a name, log base a of x. We can do some evaluations because they're inverses of the exponentials, but let's do log base 2 of x. Well, it turns out all the logarithms where the base is bigger than 1 look like this. If you look and turn your head right, this is an exponential function sort of sideways and turned around. That point is still 1. So anytime you plug 1 into a logarithm, you're going to get 0. That's a very important point to remember. And then it's very shallow growth. It doesn't grow very fast at all. But this is sort of the graph of all the base A logarithms where the base is bigger than 1. So log base 2, log base 3. And then there's a special one, the natural log, which is log base E. We just call it natural log. That's the base E logarithm. Looks sort of like this as well. And then the other way around, if we look at a base less than 1, log base 1/2, again, you can base it off of the one above, the exponential. It sort of comes along here and then looks like an exponential going that way. So sort of a sideways exponential again, and goes through 1. All the logarithms, when you plug in a 1, you'll get 0 from your basic logarithms. All of them have a domain that's just 0 to infinity. You can see the only y coordinates involved are 0 to infinity. And the range in all cases, you'll get all y coordinates eventually. So there's your basic logarithms. It's good to keep those graphs in mind. We use them over and over in calculus, especially this natural log shape that I've got here. All right, so that's 2 sets of transcendental functions. And then we got 2 more, which again, these exponentials, and then that's the inverses of the exponentials, and then we'll have the trig functions and their inverses. So I'm not going to spend much time on the sines, cosines, and all that, because it's a whole course dedicated to these. But it is important to remember the basic graph of sine and cosine. Sine graph looks something like that. That's 0 to 2 pi. This is your basic graph, and then it keeps going just like this in both directions. It has a domain of everything, even though I've chopped it off here, but that's just one period sketch. This has a range. It stays between -1 and 1. We use that a lot for sines and cosines. And then cosine is sort of just like a sine graph, except it starts in a kind of a different place. It starts here, and then it starts oscillating. And if you keep drawing it, they look alike, like one of them's just been shifted a little bit. It has the same domain and range as sine. And then we also have tangent and cotangent and all that. But the 3 main ones that we graph are sine, cosine, and tangent. So we do need to know the graph of tangent. We don't usually graph the cosecant and secant and cotangent. It's not that they're not important. They just, if you can graph these others, it turns out you can get that one. The thing about tangent is it has vertical asymptotes. So there's some points that aren't in the domain of tangent. Tangent kind of winds between there like that. This is at pi over 2 and negative pi over 2. And then over here at 3 pi over 2 and negative 3 pi over 2. And you just get this same repeated graph over and over every interval of pi. This is length pi. You get the same graph over and over. So you can see domain for tangent is that you have to eliminate all the odd multiples of pi. So I'm going to say something like this. X can't be 2n plus 1 over 2 times pi. That's odd numbers over pi, and you can pick n to be any positive or negative integer. So for example, if I plug in 0, I get pi over 2. If I plug in -1, I get minus pi over 2, and so forth. So this will generate all these places that I have to leave out of the domain. The range is everything. You can see the tangent will wind from -infinity to infinity. And like I said, there's others, the cosecant and secant and cotangent. They have graphs. We don't look at them as quite as much, or probably not at all in this class, even though we use those functions. We usually use these for our basic examples when we need to draw graphs. And likewise, the last set of basic functions that we should be familiar with are the inverse trig functions. You need to be able to do calculations with them. You need to be able to do things with them from their graph perspective. And so I just want to look at their graphs here. So if I want to draw a sine inverse, and that can also be written as arc sine. Some books, that's not supposed to be there. Anyway, arc sine of x. That's to avoid possibly reading this as an exponent. That's notation. That just means that you read that as sine inverse. It's not 1 over sine. Sine inverse, the graph looks something like this. What you do is you draw the graph of sine, but you draw it along the y-axis. So I go like this, then I could keep going if I wanted, but I'm not going to. And then I go down here, and I could keep going if I wanted to, but I don't want to, because I want to function. If I keep going, then notice I no longer pass the vertical line test. So sine inverse is sort of different. We do chop it off, and that causes some problems when you're doing calculations sometimes. But since we're chopping it off, it turns out we're only going to allow the y's go from minus pi over 2 to pi over 2. This is sort of a sideways sign. It's going to go from minus 1 to 1, sort of the opposite of what we had above. So there's your basic graph of sine inverse. So you can see the domain and the range just by looking at it. And then cosine inverse. Again, we try to draw this like we're drawing a cosine along the y-axis, and we start here this time. So I'm going to draw my cosine graph, and I don't have a problem with cosine until I get here. Then it would start coming back on itself, or here. Then I wouldn't have a function anymore. So I cut it off here at pi and at 0. And this, again, is 1, and over here is minus 1. That's your basic graph of cosine inverse. And then the one whose graph shows up the most turns out to be tangent inverse. This one is the one we use in a lot of examples throughout calculus, is tangent inverse. And it's sort of my tangent, sort of sideways, because this up above, this is going to be an asymptote. Now it's a horizontal asymptote of pi over 2 and a horizontal asymptote of minus pi over 2. And then your graph of tangent inverse sort of winds in between there, sort of looks like a sideways turned around tangent. You can see the domain of this is everything, but the range has to stay between minus pi over 2 and pi over 2. So we'll do calculations and such throughout the course with these inverse trig functions. There's some practice problems in the text, so certainly want to look through where you need to kind of strengthen your background. But that's our basic functions. We'll create new ones from these, but most of what we do will be based on all of this set of 10 types of functions throughout this course. And what we'll do next is we'll look at how we create new functions from these.